Let's see how quickly we can cover everything you need to know for AQA GCSE Chemistry Paper 1. This is good for higher and foundation tier, double combined trilogy and triple separate chemistry. That's topics 1 to 5, atoms, bonding, quantitative chemistry and chemical and energy changes. I'll tell you when something is just for triple and when some of the bigger concepts are just for higher tier. We're going to have to be moving at quite a rate here. You can pause the video if you need a bit more time to get your head around something you see. Let's go. Substances, stuff, are made of atoms. The different types or elements of atoms there are represented in the periodic table by a symbol. A compound is a substance that contains two or more different types of atoms chemically bonded together. For example, the chemical formula for water is H2O, is made up of hydrogen and oxygen atoms. For every one oxygen atom, there are two hydrogen atoms. If there's no number after a symbol, there's an invisible one there. These atoms change what they're bonded to and how they're bonded through chemical reactions. We can represent a reaction with a word equation and a chemical equation using symbols. As atoms are not created or destroyed in any chemical reaction, there must be the same number of each type of atom on both sides. So sometimes we must balance equations. Pro tip, start balancing atoms that are only in compounds. So with this one, let's go with the carbons first. There's one on the left, one on the right. So that's all good. Hydrogens, there are 4 on the left, only 2 on the right. Now we can't change the small numbers because that would change what the compound is. So what we can do is put numbers in front of elements or compounds to multiply them up. Stick a 2 in front of the H2O. We now have 2 times 2 hydrogens, so that's 4. That's also doubled the oxygens in it, however, so now we have 4 oxygens on the right, still only 2 on the left, so doubling this O2 on the left takes care of that. If there's an element in a reaction, like oxygen here, we always finish balancing that, as there's no knock-on effect. A mixture is any combination of any different types of elements and compounds that aren't chemically bonded together. For example, air is a mixture of oxygen, nitrogen and more. Solutions are mixtures too, like salt water, a mixture of water and sodium chloride. You can separate large insoluble particles from a liquid using filtration, like sand from water, as sand can't dissolve. Crystallization can leave a solute, that's the solid dissolved in a liquid, behind after you evaporate the solvent from a solution, like salt from water. Similarly, distillation involves heating the solution as well, but this time the gas is cooled so it condenses back into a liquid. You can also do this at different temperatures to separate the different liquids of a mixture, as they will have different boiling points. This is called fractional distillation. These are all physical processes though, and not chemical reactions, because no new substances are being made. Solid, liquid and gas are the 3 main states of matter. For example, water can be ice, a solid, where the particles, or molecules in this case, vibrate around fixed positions. It can also be liquid water, where the molecules are still touching but are free to move past each other, and it can also be a gas, water vapor we call it when it's water, where the particles are far apart and move randomly, and they also have the most energy and so move quickly. As molecules in a gas are far apart, gases can be compressed, while solids and liquids cannot. To melt or evaporate a substance, you must supply energy, usually in the form of heat, to overcome the electrostatic forces of attraction between the particles. We don't say we're breaking bonds in this case. Note that none of these make a new substance, so these have to be physical changes again, not chemical reactions. We're not breaking any chemical bonds. In chemical reaction equations, we indicate what state a substance is in with state symbols. Brackets S for solid, L for liquid, G for gas, and also AQ for aqueous. That means dissolved or in solution, again like salt in water. The idea of what atoms are like came about gradually. J.J. Thomson discovered that atoms are made up of positive and negative charges. He came up with the plum pudding model of the atom, a positive charge with lots of little electrons dotted around it. It was Ernest Rutherford who found that the positive charge must actually be incredibly small. We now call this the nucleus, and the electrons must orbit relatively far away from it. He discovered this by finding that most alpha particles fired at a thin leaf of gold atoms went straight through, proving that atoms must be mostly empty space. Niels Bohr later discovered that electrons exist in shells or orbitals. Then James Chadwick discovered that the nucleus must also contain some neutral charges. He called them neutrons, while the positive charges are called protons. Protons and electrons have equal and opposite charges, so we just say they're +1 and -1, relatively speaking. Neutrons have a charge of 0. Protons and neutrons have essentially the same mass, so we say they have a relative mass of 1. Electrons are very light in comparison, so we say they have a mass of 0 or just very small, depending on the situation. The periodic table tells us everything we need to know about an atom. The bottom number is the atomic number. That's the number of protons in the nucleus. This is what determines what element you have. Every atom has an overall neutral charge, so that means they must have the same number of electrons as protons. If an atom gains or loses electrons, it's now called an ion, not an atom. The top number is the mass number, or relative atomic mass, or RAM for short. It tells you how many protons and neutrons are in the nucleus, so that must mean that this carbon atom, carbon 12, has 6 neutrons on top of its 6 protons to make that 12. However, you can get a carbon atom with 7 neutrons instead, so its relative mass is 13. These are what we call isotopes, atoms of the same element but different numbers of neutrons. You might see a number that isn't a whole number for the mass. This is because periodic tables sometimes show the average mass for all of the isotopes of that element found in the world. For example, if you have some chlorine gas, it turns out that 75% of the atoms will have a mass of 35, while 25% of the atoms will be 37. These are what we call their relative abundance. To find the average, we just pretend that we have 100 atoms, we add up the total masses of all the isotopes, then just divide by 100. That's why chlorine's average relative atomic mass is 35.5. The periodic table is incredibly useful, but how was it made? Before it, scientists just put elements in order of their atomic weights. Some were then grouped together if they were seen to have similar properties, but still using the atomic weight order. Dmitri Mendeleev then came along and grouped elements together based on their properties, even if the order didn't follow atomic weight. Using this method, he found there were gaps in his table. He asserted that these elements were yet to be discovered. In time, he was proven correct, showing that his table was indeed correct. Like we said, electrons exist in shells around the nucleus. The shells fill up from the inside with a maximum of 2 on the first shell, 8 on the second and third shells. Then we only go to 2 on the fourth shell. That's 20 electrons altogether, which brings us to a calcium atom. After this, we get into the transition metals, where things get a little bit crazy, so we leave that until A-level chemistry. So we only care about the electron configuration going up to 2882. Magnesium has 12 electrons, so its electron configuration, for example, will be 282. The modern periodic table can be split up into different sections. For example, everything to the left of this staircase is called a metal. Metal atoms always donate electrons to gain an empty outer shell of electrons. Again, slightly weird with transition metals, but we don't think about their shells. To the right of the staircase, non-metals. They always accept electrons to gain a full outer shell. The column an atom is in is called the group. It tells you how many electrons an atom has in its outer shell. Again, the transition metals work in a really weird way, so they don't get their own group. In fact, it turns out this is because they can donate a different number of electrons when they bond to different things. The atoms in group 1 are called the alkali metals. They all have 1 electron in their outer shell, which they give away, donate when they bond to something. So they have similar properties, like when they react with water. The further down the group you go, though, the further that outer electron is from the nucleus. So the electrostatic attraction is weaker between the negative electron and the positive nucleus. This means that the electron is more readily donated. This means the metals get more reactive as you go down the group. Group 7 are what we call the halogens. They're essentially the opposite. They have 7 electrons in their outer shell, so they need 1 more to gain a full outer shell. The further down the group you go, the less readily an electron is accepted onto that shell that's further away from the nucleus, so they get less reactive down the group. Their boiling points also increase down the group too. Group 0, sometimes referred to as Group 8, are called the noble gases. They already have an empty or full outer shell, just depends on your perspective, so they don't react. In reality, they can react under special conditions, so we just say they're very unreactive. We don't really say group 8 anymore though, because some people thought that helium might feel a little left out, as it only has 2 electrons in its outer shell. As electrons are negative themselves, metals become positively charged when they lose them. They always form positive ions. All of group 1 lose 1 electron when they turn into an ion, so all of their ions are 1+. But again, we don't write the 1, we just put plus. Group 2 lose 2 electrons to get an empty outer shell, so their ions are all 2+. Group 7 gain 1 electron each, so all their ions are minus. Group 6's ions are all 2-. The atoms in group 3, 4 and 5 don't really form ions, except for aluminium, which is 3+. Like we said, transition metals can donate different numbers of electrons. For example, an iron ion can be Fe2+ or Fe3+. It can donate 2 or 3 electrons. So we give them the names iron 2 and iron 3 to distinguish between them. Transition metals are generally harder and less reactive than the alkali metals. They also form coloured compounds. Bonding next. Metal atoms bond to each other through metallic bonding. Essentially a lattice or grid of ions is formed with a sea of delocalized electrons around them. Delocalized just means they're not exactly on the atom. As these electrons are free to move, metals make good conductors of electricity and heat. Metals bond to non-metals through ionic bonding. Like we said, a group 1 metal needs to lose an electron, while a group 7 atom needs to gain one. It's a match made in heaven. For example, a lithium atom donates or loans its outer electron to the chlorine. We can draw a dot and cross diagram to show where the electrons end up. You can choose which one belongs to which. We only need to draw the outer shell for each. Don't forget to put brackets and the charge of the ions when it comes to ionic bonding. The charges of all ions in an ionic compound must add up to 0, so Li plus and Cl minus is all good. So this is the chemical formula for it. Same with beryllium oxide, Be2 plus and O2 minus. Beryllium chloride, on the other hand, well, the beryllium needs to lose 2 electrons while a chlorine only needs 1. So that means there must be 2 chlorines or chloride ions for every beryllium. So Be2 plus and 2 lots of Cl minus adds up to 0. So that means the chemical formula is BeCl2. Sorted. Ionic compounds consist of lots of repeating units of these ions in a lattice to form a crystal. They have high melting points and boiling points due to the strong electrostatic forces that need to be overcome. And they can conduct electricity but only in liquid form, that is molten, or when dissolved in solution. And that's because the ions are free to move in both cases and they carry charge. You can also get molecular ions. For example, OH minus is a hydroxide ion and consists of a hydrogen atom and an oxygen atom. So magnesium would need 2 of these to make magnesium hydroxide. Here are a few other examples. By the way, I spell sulfate with a PH instead of an F because I'm stubborn and refuse to adopt the American spelling. You'll get the mark either way. Any ionic compound can be called a salt, not only sodium chloride, your table salt. The name is always the metal ion, positive ion or cation we can call it, followed by the non-metal ion or anion. Anion names are different from their normal names. Like we've just seen, it's not sodium chlorine but sodium chloride. Some people remember which way around cations and anions are by liking cats, and they say cations are positive. Non-metals bond to each other with covalent bonding to form molecules. They do this by sharing electrons to gain full outer shells. For example, chlorine gas is Cl2. Each chlorine atom shares an electron with the other, so they're both happy. Never write down happy in the exam though. Here's the dot and cross diagram. We can also draw the structural formula for molecules with just symbols and lines. We could also say that every one of these represents a dot cross electron pair. Each oxygen needs 2 extra electrons, so O2 is a result of each oxygen atom sharing 2 electrons each. As such, this is a double covalent bond. Nitrogen, N2, is one of the few molecules with a triple bond in. In covalent bonding, the number of electrons an atom needs is the same as the number of bonds it must make. Hydrogen can only ever make 1 bond, carbon makes 4 bonds, etc. Here's a few more. If you're not in a rush, pause the video and have a go at them. And here are the answers. These above are what we call simple molecular or simple covalent structures, individual molecules that can all mix together. These have relatively low boiling points as there are only weak intermolecular forces between them that need to be overcome with heating. Be careful though, that's not covalent bonds being broken like we said, and unlike ionic compounds, these can't conduct electricity, even as liquids. Giant covalent bonding is similar to the lattice nature of ionic compounds. Atoms form covalent bonds to other atoms, which form bonds to other atoms, and so on, until what we have in effect is one giant molecule. Diamond is an example of this. It's a crystal of carbon atoms bonded to each other. That's why it's so hard and has such a high melting point. You would have to break the covalent bonds in order to do that, and they're incredibly strong. Graphite is only made of carbon as well, but it's not diamond, so it's an allotrope of carbon. Made out of the same atoms, bonded together in a different way. Graphite consists of layers of carbons with 3 bonds each in a hexagonal structure. Where's the 4th bond though? Well, the spare delocalized electrons form special weak bonds between the layers, which means that it can conduct electricity because the electrons can move between the layers as well. And it also means the layers can slide over each other easily, which is why it's used in pencils. As a side note, metal alloys are stronger than pure metals. Having mixtures of metals means that we have different size atoms, and that disrupts the regular lattice so layers can't slide over each other as easily. Back to carbon allotropes, graphene is just a single layer of graphite. Fullerenes are 3D structures of carbon atoms. For example, Buckminster fullerene is a spherical football-like structure consisting of 60 carbon atoms each. Fullerenes that have a tube shape are called nanotubes. Just for triple real quick, surface to volume ratio is just 1 divided by the other. If the length of a side of a cube doubles, that means this ratio halves. As nanoparticles are tiny, this ratio is huge for them, which means that fewer could be needed to fulfill a purpose compared to larger ones. Quantitative chemistry next, some tricky stuff coming up. Total mass of all substances is conserved in a chemical reaction. Like we said earlier, that must mean the atoms that go in must come out, so we must balance equations to that end. We already know about relative atomic mass, but if it's a compound, we can add these up to give the relative formula mass. We just add up the individual rams. So CO2 is 12 plus 2 lots of 16, so that's 44. Some reactions produce a gas product, which, if it leaves the reaction vessel, will result in a seeming decrease in mass of the reactants. A mole is just a specific number of atoms or molecules, but we don't really need to know the number. It's just a way of comparing amounts of substances, as we can't deal in individual numbers of atoms or molecules. If you're foundation, you don't need to deal in moles, by the way. If you have as many grams of a substance as its relative atomic or formula mass, you have 1 mole. So 1 mole of carbon has a mass of 12 grams. That means we calculate the number of moles of something we have like this. Moles equals grams over rams, where rams is short for relative atomic mass, but it also could be relative formula mass. This is an equation worth remembering. Let's take our methane combustion reaction from earlier. Like we said, in order to balance this, we'd need 2 oxygen molecules per 1 molecule of methane. This is also true for moles too then. We'd need double the moles of oxygen to methane. So here's how a question could go. How many grams of water would be made if 64 grams of methane reacted completely with oxygen? We need to get from the mass of one thing to the mass of another, so we use moles as the middleman. The process is this: mass, moles, moles, mass. We switch from one to the other at the halfway mark. So, a mass of 64 grams of methane. How many moles is that? Moles equals grams over rams, so that's 64 divided by 16. That's 4 moles of methane. But look, there's no number in front of the methane, but there is a 2 in front of the water, which means we must have double the moles of water. So that's 8 moles. By the way, we can say that the stoichiometry is 1 to 2. That just means the ratio of moles of one substance to another in a reaction. So all we have to do then is turn that back into mass using our equation by rearranging it. Put it into a triangle if you have to and cover up mass. Grams equals moles times rams, so that's 8 moles times water's ram of 18. That's 144 grams of water made. You could also be given the mass in kilograms or even tons. The great thing is that because this is all relative, we can just put those masses into our equation instead of grams. And so long as you stick with that unit for the whole question, you'll still end up with the right answer. Of course, we can also use moles to predict how much of a reactant we would need in a reaction. As you can see, we need 2 moles of oxygen to every 1 mole of methane. If we had that 1 mole of methane, but only 1 mole of oxygen, that means that not all of the methane would react. Some would be left behind. We say that the oxygen is the limiting reactant in this case. It ran out first. The concentration of solutions can be given in grams per decimeter cubed, where a decimeter cubed is 1000 centimeter cubed. But it's often useful to convert this into moles per decimeter cubed instead. If 1 mole of HCl is dissolved in 1 decimeter cubed of water, we've made hydrochloric acid at a concentration of 1 mole per decimeter cubed. Sometimes we shorten this to just 1 mole. Well, people, wake up, this is chemical changes. We saw briefly earlier that metals vary in their reactivity, as some donate their electrons more readily than others. Here's the reactivity series for the most common metals we consider. You can see that hydrogen and carbon have also snuck in there. That's because it's often necessary to compare the reactivity of metals to those in order to predict what will happen in a reaction. A more reactive metal will displace a less reactive metal from a compound, that is, kick it out. For example, if you place zinc in copper sulfate solution, you'll see copper forming on the lump of zinc. The zinc displaces the copper to form zinc sulfate, kicking the copper out of the compound. We know that alkali metals react with water. The reaction happens because, for example, potassium is more reactive than hydrogen. So in essence, it displaces it from the water, leaving potassium hydroxide, and hydrogen gas is produced. We can use this when it comes to extracting metals from their ores found in the ground. Any metal less reactive than carbon can be displaced by it. For example, iron can be displaced from iron oxide with carbon. This is called smelting. We can also say that the iron oxide has been reduced. It's the opposite of oxidation, because oxygen is lost. Even if oxygen is not involved in a reaction, we can still say that reduction and oxidation happen depending on whether a reactant loses or gains electrons. The mnemonic is oil rig. Oxidation is loss, reduction is gain, of electrons, that is. The iron ions in the iron oxide are positive, of course, because they're metals, and they gain electrons to turn back into atoms. They become neutral. They've been reduced. Here's the half or ionic equation for this. We should never really have a minus in any half equations, so think carefully about which side the electron should go on, depending on whether it's oxidation or reduction. Metals more reactive than hydrogen can displace it from an acid, so most metals react with hydrochloric acid and sulfuric acid, for example. This produces a salt. Alkalis, they have a pH greater than 7, react with acids, less than 7, to produce a salt and water. If the quantities used are correct according to their stoichiometry, they will neutralize each other completely to leave no unused reactants. Here's an example. Sodium hydroxide and hydrochloric acid makes sodium chloride and water, neutral, pH of 7. If sulfuric acid is used, a metal sulfate is made, nitric acid, metal nitrate. These salts are left in solution, that is dissolved in water. When any substance dissolves, its ions partially dissociate, as does the water actually, into H+ and OH- ions. We can obtain solid crystals of a dissolved salt by warming gently so the water evaporates. The pH scale is a logarithmic scale, base 10. It's not linear. What does that mean? Well, an acid contains H+ ions, and an acid that has a pH of 3 will have 10 times the concentration of these compared to an acid of pH 4. pH 3 would have 100 times the concentration of H+ ions compared to an acid of pH 5, and so on. Alkalis work in a similar way, but with OH- ions instead. The higher you go, the greater the concentration. A strong acid is one that dissociates or ionizes completely when in solution, like hydrochloric, nitric and sulfuric acids. Weak acids, on the other hand, only partially dissociate, like ethanoic, citric and carbonic acids. The pH of an acid depends on both its strength and concentration. If hydrochloric acid and ethanoic acid have the same concentration, the hydrochloric acid will have the lower pH, as it's stronger. Electrolysis is for everyone. If you melt an ionic compound, let's say aluminium oxide, it can conduct electricity as the ions can move. We know that from earlier. By passing a current through it using inert electrodes, that means they won't react, like carbon, the positive metal ions, or cations, Al3+ in this case, they move to the negatively charged electrode, we call that the cathode, where they receive electrons and turn into atoms. Cations are always reduced at the cathode. So in this case, solid aluminium is formed on the cathode. The negative ions, or anions, O2- in this case, move to the positive electrode, the anode, where they lose electrons. In this case, oxygen gas, O2, is formed. Anions are always oxidized at the anode. This is one way of purifying metals or extracting them from compounds, say if displacing with carbon isn't an option due to their reactivity. In this case of aluminium oxide, the oxygen produced at the graphite carbon anode reacts with the anode itself, so these need to be replaced every so often. Again, specifically for this case, aluminium oxide is mixed with cryolite to reduce its melting point, making it cheaper to extract the aluminium. We can also do electrolysis with ionic substances in solution, say sodium chloride solution. We know that the solution is a mixture of Na+, Cl-, H+, and OH- ions, as they're all partially dissociated. But what will be attracted to and reduced at the cathode, the Na+ or the H+? Well, it comes back to reactivity. The more reactive ion stays in solution, while the less reactive one moves to the electrode. That's the H+ in this case. That's why hydrogen gas is made at the cathode here. If the metal is less reactive than hydrogen, say copper in copper sulfate solution, it forms on the cathode instead, and the H+ ions stay in solution. That actually makes an acid. If there is a halide ion present, like the Cl- here, it is oxidized at the anode. If there's no halide ion in solution, the oxygen from the OH- is oxidized instead, and oxygen gas is produced. Finally, energy changes, hopefully a short one to finish off. Any chemical reaction involves energy transfers, as energy is needed to break chemical bonds, while energy is released when chemical bonds form. Both of these happen in any reaction. If there is more energy released from bonds made than energy needed to break bonds, we say this is a net energy released, and we should observe an increase in temperature as a result. This is an exothermic reaction, for example, combustion. The way I think about it is explosions are exothermic. I mean, the X just means out. If it's the other way around, there is net energy input into the reaction, so the reaction should get colder. This is an endothermic reaction. The practical on this goes as follows. We carry out a neutralization reaction between an acid and alkali in a polystyrene cup, which is well insulated, and a thermometer poked through a lid that sits on top. We measure the maximum temperature the reaction reaches, then increase the volume of alkali used and repeat. Eventually, the maximum temperature will not get any higher due to all of the acid reacting, and the same amount of energy released is being shared across a larger volume of liquid. We can draw two lines at best fit for the rise and fall in these max temperatures. Where they meet tells us how much of the alkali was needed to neutralize the acid. We can use an energy profile to help us visualize the difference in energies between the reactants and the products. Now, this is something that people get confused with. The y-axis is potential energy. And you should know that usually in science, potential energy and kinetic energy do a balancing act. If one goes down, the other one goes up. So if the potential energy of the products is less than the reactants, they must have gained kinetic energy. And that always means a hotter temperature. This is an exothermic reaction. It might seem like the energy has gone down, but kinetic energy has increased. Of course, fuel must need a spark to start it burning, which is why we draw this bump to represent the activation energy, the energy needed to get the reaction started. Here's an energy profile for an endothermic reaction too. Every bond needs a very specific amount of energy to break. For example, a carbon-hydrogen covalent bond needs 413 kilojoules for every mole of these to break them. If a mole of these are made, it's the same amount of energy released. So let's take our combustion of methane equation one last time and draw the structures so we can see all the bonds. We need to break all of the bonds in the reactants first, so that's 4 lots of 413 and 2 lots of 495 for the 2 lots of oxygen double bonds. So that's 2,642 kilojoules per mole needed to break all of the bonds. The unit isn't that important, by the way, we're more interested in the numbers. Making bonds, on the other side, 2 times 799 is released when the CO2 double bonds are made. Plus 4 lots of 467 for the 2 water molecules. That's 3,466 kilojoules per mole released. By the way, you'll always be given these numbers, you don't need to remember them. More energy is released than goes in this case, so it's exothermic. That checks out, doesn't it? One minus the other gives us the net energy released, and in this case that's 824 kilojoules per mole.